So today we're going to see another way for determining an unknown concentration of a solution through the method of a titration. And there we have an acid-base titration and how to do calculations after we complete the titration. So this is not as difficult as it sounds, actually. So you see acid-base. Why acid-base? When we react an acid with a base or an alkali, this is a neutralization reaction. So, I mean, if we have the reaction of an acid plus a base or alkali, the result is a salt and water. Salt and water. And this is a neutralization reaction. What does it mean? That the result will be neither alkaline or acidic solution, but provided, of course, that we use the correct amounts of the acid and of the alkali. Usually these are in solution. So I should say alkali here, most often. All right, so this is a neutralization reaction, and this is the reaction that a titration method is based upon. So we can do a titration to find the concentration, the unknown concentration of a solution. And a titration is an experimental procedure. I have a video to show you about this procedure, but maybe we can discuss it a little bit to introduce it. So this diagram here roughly shows how we perform a titration. You see here, this is a conical flask with some known volume. We are going to see titrations using here an alkaline solution of known concentration, which we call the standard concentration, because it's a concentration that we know for sure and we have measured very precisely. So this is called a standard solution. We're going to use a base here in our case. And here in the burette, we add the solution of which the concentration we want to measure. So if here we have the basic solution, in other words, the alkaline solution, here in the burette, we're going to place the acid solution of which the concentration we need to find out. And so this is the burette, this is the conical flask. It's a couple of things more that we need to add here, but you're going to see in the video. And the important aspect here is that since we are going to add acid in this alkaline solution, how are we going to know when we have reached the neutrality of the two? And for that reason, to help us understand when we have reached neutrality, we are going to add a few drops of some indicator. Usually, if what we have in the flask is the base or the alkali, then we add a few drops of methyl orange, usually. Methyl orange, that will be our indicator. And when we add a few drops of methyl orange in this alkaline solution, it turns yellow. And when we add enough acid to neutralize it, it will change color to red. So from yellow it will change to red. And then once we reach the point where it changes color to red, we know that it has been neutralized, and this is how we know. Instead of methyl orange, we can use also phenolphthalein, another indicator, but this indicator is used mostly if we have here acid instead of an alkaline solution, but it's not like a rule. Anyway, so in case of me talking too much, let us watch the video and then we can talk some more. Here it is. Okay. The volume is Okay, let us watch.
To work out the concentration of an unknown solution. And we use some specialist bits of glassware, which I'm going to explain how they're used and why they're used particularly. So for this experiment today, we're going to look at the reaction between a sodium hydroxide solution, and we know the concentration of this one. It's 0.1 mole per decimeter cubed, and a sulfuric acid solution, and we don't know the concentration of this one. We know it's around 0.05 mole per decimeter cubed, but we don't know the exact concentration. And so this method allows us to work that out. So the first thing we're going to do is we're going to measure out an exact volume of our sodium hydroxide solution. Now, when we want to measure out an exact volume, the correct piece of equipment to use is a pipette. And this is a pipette. Pipettes are not those plastic dropper things that you've been using since year 7. This is a bulb pipette, and it is being designed to measure exactly 25 centimeters cubed of solution when used correctly. Now, we can't just suck the solution up into the pipette using our mouths. We used to. When I was young, that was sort of the way we were meant to do it. But obviously, health and safety says we can't suck sodium hydroxide into our mouths. So we now use safety fillers. They come in a variety of different forms, but these are the ones that we most commonly use. And the way we work them is we attach the safety filler to the top of the pipette, but we don't want to hold our pipette down here and jam on the filler like that, because there's always the risk of the pipette snapping and going into the palm of our hand. And I have actually seen that happen, and I've seen the end of a broken pipette in someone's hand, so we don't want to do that. So the way we get around that is we hold right at the top of the pipette, and then we just firmly push and twist the filler on, just so it's kind of holding it firmly, okay, but it's not jammed on too tight. So we can put our pipette into our sodium hydroxide solution, and then the little wheel on the side allows us just to suck the solution, and you can see the level of it rising here, into the pipette. Obviously, it travels more slowly through the fat bit and then goes rapidly up the thin bit as we go past. There we go. Now, if you take the level almost all the way to the filler, so it's here at the moment, and then take your filler off quickly, we can see that here there is a line, and we need to get our level of sodium hydroxide exactly on that line, and then we know we've got 25 centimeters cubed. So to bring the level down, we need to just release the pressure on the top of the pipette. Now, if you look closely, you might see that the surface of the sodium hydroxide is actually curved, and that's because water is very slightly sticky. So it sticks to the sides of the tube and creates this curved surface known as a meniscus. And we need to get the bottom of the meniscus to sit on the line. So we bring it down to our eye level, we raise it off the bottom of the beaker, and then just twist it gently on our thumb, and that lowers it exactly so it's on the line. We can then just take our thumb off and run it into the flask. Now, as it reaches the end, you just let those last couple of drops out, but you might see that there's a small amount of sodium hydroxide still in the tip of the pipette. Now, you don't blow that bit out, because when the piece of glass was made, that tiny bit that stays at the end was taken into account. So if you blow it out, you actually add more than 25 centimeters cubed. So we just let it drip, and then we take it out and lay it down. So that's taken a known volume of our sodium hydroxide of known concentration, and we've put it into our beaker. So we're now onto our second solution, which is our sulfuric acid. Now, we don't know the concentration of this, remember, and we're going to place that in our burette. Now, our burette is a graduated piece of glassware, so there is a scale on it, so it can measure different volumes, and we fill from the top. Before we fill, we need to make sure our tap is closed, and the tap, I hope you can see this, is vertical when it's open, and if we twist it to horizontal, it's then closed. So we need to make sure it's closed before we start filling. the other important thing is we don't fill above eye level because we don't want to accidentally spill sulfuric acid in our face. So we bring this burette down as low as we can. And if necessary, we can put it on a stool next to us. But I think I can just about reach. Put a funnel in and then slowly pour the sulfuric acid into the burette. The 0 is at the top because it's how much we've added, not how much we've put into the burette. So once you've gone over the 0 mark, just raise the burette up a little bit and open the tap while looking at eye level and let the level of the acid go down so it is exactly sitting on the 0 mark. Again, there is a meniscus, a curved surface to the acid, and you want the bottom of the meniscus to sit on the 0 line. So now I've got my unknown acid in my burette, and I need to know what volume of this acid reacts with my 25 centimeters cubed of 0.1 molar sodium hydroxide. So I raise my burette up just a little bit, put a white tile underneath, and then the flask of sodium hydroxide can go under the burette. Before I do that, I'm going to add some pH indicator. This is methyl orange, and different indicators work for different types of titration, but this one works well for this one, between sodium hydroxide and sulfuric acid. And you'll see that in the sodium hydroxide, it's a yellow colour. So popping that underneath. The first titration we do is always a rough titration. So we just need to know roughly what volume of the acid I'll need to add. So to do that, I'm going to open the tap with my left hand and I'm going to swirl with my right hand. And I'm going to look for a sign of a colour change, a permanent colour change in the flask. And that'll show me the end point. So I open up the tap and I swirl. As you approach the end point, you will probably start noticing a pink colour appearing in the middle of the flask, but that's not the end point, because even if I get a bit of pink, if I swirl it, it goes back to yellow. It's that permanent pink that I'm aiming for. Now it looks like I'm doing it fast, that's because this is rough. Oh, I'm nearly there, just disappearing, just a little bit more, I think. There we go. You see the obvious colour change as I reach the end point. Now again, looking at my burette, I can measure how much solution has gone in. Reading from the bottom of the meniscus, that is 14.3 centimetres cubed. Each little graduation being 0.1 of a centimetre cubed. So having done the titration once roughly, I know.
Okay, guys, that's enough. Now, at least you have an idea of how the titration happens. This was the first rough titration. She's going to repeat now more carefully when she arrives at the top, near the end point, near this volume that she measured. She's going to stop the tap and only allow drop by drop the acid to fall so that she has a better reading. But the idea is to see what equipment is being used in the titration, to see the color as well, the color of the indicator when it's mixed with an alkaline solution, and what happens when the acid neutralizes the solution. I hope you saw that from yellow it turned to this reddish color, and this is enough because we now need to see about the calculations that are involved in the titration. Okay, and if you want, we can continue with this video even next week. But now let us continue with our calculations now. So I see your comment there. It's going to change the indicator color. It will turn a red, pink. Yes, exactly. When the acid kind of neutralizes the base, it will, the color of the solution will turn pinkish red. Yes. This is the this video that we saw now. And here I just have the two types of indicators that most likely we're going to meet in the titrations. Here, the bottom picture shows the methyl orange. When it is in here in a basic solution, in an alkaline solution, it's yellow, and once it becomes when it changes, it becomes neutral, it changes into this reddish pinkish color here. So this is with a methyl orange, but we could also use phenolphthalein, which if this indicator, a few drops of it inside an alkaline solution, it's pink. But when it changes color and or when it is in acid, it looks colorless like this. So when we add the phenolphthalein in acid, it's colorless, and if we add a basic solution, it reaches a point where it changes into pink, and vice versa. So these are the changes from pink to colorless or from yellow to red. So these are just to have an idea of how these indicators work. Now that we have an idea of the procedure of the titration, why do we do the titration? Is for us to measure as accurately as possible the volume of the acid of whatever solution we have in the burette, so that we know exactly which volume we have used to neutralize the already known volume of the basic solution that we had in the conical flask. And if you remember, the solution had the volume, I mean, the alkaline solution in the flask had the volume of 25 cubic centimeters, because this was the volume that this lady measured with a pipette, isn't it? It had even a marking there to exact 25 cubic centimeters. So here is an example for of a question that we can find on titration. Say that we made the titration between hydrochloric acid and the sodium hydroxide. We had the sodium hydroxide in the conical flask. We measured its volume, was 25 cubic centimeters exactly. We knew this is a standard solution, so therefore we knew its concentration was 0.1 moles per cubic decimeter in this case. And then we did the titration, and we found that a volume of 20 cubic centimeters of hydrochloric acid neutralizes exactly this solution of sodium hydroxide. So this is the measured volume that was necessary to neutralize this solution of sodium hydroxide. So these are the numbers usually that we get when we are dealing with a titration. We have the volume of the solution that is in the flask and its known concentration, and then we find out how much volume is necessary to neutralize the solution. So right now, what do we do? Look at this. We are talking about finding the unknown concentration here of the hydrochloric acid in this case. What is the formula that we have learned about concentration? Concentration of a solution is equal to the amount of solute in the solution divided by the volume of the solution. So that was the amount of solute, and this is the volume of the solution. All right, so in this case now, look at the sodium hydroxide. We know its concentration, we know its volume, we can find the number of moles that are found, the amount of sodium hydroxide base that is found in this particular volume. So here we can do the calculations. This number of moles, here if we solve for n, what is n? Is concentration times volume, isn't it? Concentration times the volume. We have these values here. The concentration of this solution is 0.1 moles per cubic decimeter, and the volume is 25, but be careful, we need to change this into cubic decimeters here, so we have to divide. And this, if we do the calculations, I should find my calculations here. Yep, here it is. 25, yeah, that's the one. It's okay, it's 2.5 times 10 to the power of minus 3 moles per cubic moles. Sorry, this is number of moles. Okay, so 2,5 times 10 to the power of minus 3 moles of sodium hydroxide. Now, of course, here is the chemical reaction equation. It's already balanced, and we see that the acid and the base react in a ratio 1 to 1, isn't it? So since we know the moles, the number of moles of sodium hydroxide, obviously the same number of moles must be the moles of the acids that have reacted. So this is also, in other words, the same n here. If this is 0, if this is, sorry, not 0, 2,5, it's 2,5. We found that this is 2,5 times 10 to the power of minus 3 moles. The same moles will be there, 2,5 times 10 to the power of minus 3 moles as well. So now we know the amount of the acid, we know its volume because this is what we measured, and we can find now its unknown concentration. So now the concentration of this acid is amount divided by volume. So this is 2,5 times 10 to the power of minus 3 moles divided by its volume, which is 20 cubic centimeters. Remember, we need to change it into decimeters cube. And here, which is nice because this cancels, isn't it? So it's 2,5 divided by 20, and how much is that? 0,125 moles per cubic decimeter. And this is the unknown concentration of the acid. So this is how we use the method of titration to calculate eventually the concentration of the unknown concentration of the acid, which we had in the burette, isn't it? So this is how it works. Okay. I hope. All right. So now let us see another example. All the examples are very similar. Here we are, another example. This time we have now 10 cubic centimeters of sulfuric acid. So here's the volume of sulfuric acid is given, is 10 cubic centimeters. Neutralized 25 cubic centimeters of calcium hydroxide. So neutralized this volume of 25 cubic centimeters of calcium hydroxide of concentration 0,2 moles per cubic decimeters. So the concentration of this one, of this calcium hydroxide, is 0,2 moles per cubic decimeter. Okay. Calculate the concentration of the acid. What is the concentration of the acid? All right, we do the same thing. Remember, three quantities are important for each for the acid and each for the base. What else is here? From this information, we can find the number of moles of calcium hydroxide. By the way, this reaction is already, the equation that is already balanced. Okay, so it's again, the acid and the base, it happens to be again in a ratio of 1 to 1. So whatever number of moles we find for the hydroxide, the same number of moles will be for the acid. Okay, so here we can do the calculations. Remember that generally, concentration is amount over volume, isn't it? So solving for amount, we have concentration times volume. Concentration here is 0,2. The volume is 25. And remember, change it into cubic decimeters by dividing by 1,000. And let's see now, we can find the calculations here. Do I have these calculations? What is this? Yep. Yeah, I found 0,005. 0,005 moles. All right. If you find any mistake, just let me know. So these are the number of moles of calcium hydroxide. Obviously, the same number of moles are the ones that react concerning the acid. sulfuric acid. So this then, because it's in a ratio of 1:1 from the stoichiometry of this reaction, this is also 0,005 moles. So we have the amount of the acid, we have the volume of the acid. Now we can find the unknown concentration of the acid, which is amount over volume. The amount is 0,005 moles. Volume is 10, and change them to cubic decimeters. And these calculations here will give us that this is 0,5 moles per decimeters cubed. So this is the unknown concentration. This is the same thing again. In fact, I even found a problem from a past exam paper. Maybe for next week we can do it. They're all along the same lines. Let us find a problem where the ratio between acid and base is not 1:1, but it's something different. Let's see. Like this one. Okay. Same thing again. 20 cubic centimeters of hydrochloric acid. So the volume of the hydrochloric acid is 20 cubic centimeters. Neutralize 25 cubic centimeters of the base of calcium hydroxide of concentration of 0,1 moles per cubic decimeters. The standard solution. Calculate the concentration of the acid. Okay. Same thing. We have the volume. We have the volume of this standard solution. We have the concentration of this standard solution. We can find the amount of the base here, the amount of calcium hydroxide. So the amount is, again, we remember, C times concentration times volume. Concentration is 0,1 times the volume, which is 25 times 10 to the power of minus 3 decimeters cubed. And what is this now? 20, yeah. Okay, this is about, according to these calculations of mine, is 0,0025 moles. Okay. Now, but now this number of moles here, the ratio here is 2:1. So if we have 0,0025 moles of calcium hydroxide, obviously this react with double the number of moles of the acid. So what is our number of moles for the acid? Is twice this number, isn't it? So this is 2 times 0,0025 moles. All right. So now that we know the number of moles, we can find the unknown concentration again. What is this now? Concentration is amount, which is 2 times 0,0025 divided by the volume, which is 20 times 10 to the power of minus 3. Okay, good. What is the answer there? I think this is 0,25. I hope I'm looking at the correct answer here. Moles per cubic decimeter. Okay, so there it is. Once again, sometimes we might need to find, they might ask us to find the concentration in terms of grams, per volume, rather than moles per volume. But we can do that once we have this concentration in moles per cubic decimeter. We can change the moles into grams. We can do something like that next week. Okay, so we can do a couple more examples next week, including something from a past exam paper to see how they look like. And you see, it's not really anything difficult. would you mind please, I'm reading your message, would you mind please possibly sending me the lesson?